Hello, welcome to Emergent States of Matter, and we are going to be talking today about pattern formation, and we're going to go into the nonlinear theory of pattern formation, something which we have avoided so far. So let's just recap from the last lecture. So what we saw last time was we introduced the idea of a neutral stability curve, below which, as a function of the parameters and wave number, the system had a uniform state that was stable, spatially uniform state. And as we go above that curve, what we find is a transition to a state with patterns, meaning a state with spatial variation. And those patterns we are calculated from linear stability analysis. So what we did last time was we looked at small perturbations of the uniform steady state and discovered the conditions in wave number and parameter values under which the real part of the growth rate of the pattern was positive. And that gave us this picture that you can see on the left as a function of the control parameter R and Q, R being the Rayleigh number for convection. And then, of course, we then had to consider what happens when you look at the pattern that is formed and ask whether it itself is stable to small perturbations. And we didn't do the calculation for that. But what I reported to you was the result of detailed calculations done about 40 years or so ago by various people, showing you what is known as the Busa balloon, the region of stability in this Rayleigh number and wave number phase diagram. And you can see that there are states where the periodic pattern is unstable to what? The analysis doesn't tell us. And in the middle is a stable region where the periodic state is indeed linearly stable. And then what we did was we looked at some of the instabilities that can arise. One of those instabilities was the Eckhouse instability, which is a modulation of the wave number. And that was the instability that is listed on the right of that Busa balloon. The other instability is the zigzag instability, which I show over here. And in both of these cases, what we're doing is we're characterizing the pattern and the stability by two wave numbers, little q, which is the actual pattern itself, and big Q, which is the wave number of the perturbation. So let me just set my timer here. So we're going to now look at what happens when we go into the nonlinear regime. So let's do this. Let's do that. All right. So let's get started then. And so this in my notes is section 6 of this chapter, which is the nonlinear theory for pattern dynamics. Now, if I had unlimited time, what I would do is I would derive all of this stuff by renormalization group methods. But of course, I'm not going to do that for this course. So we're going to restrict ourselves to quick and dirty ways that give us the right answer. And so we'll have to be content with that for this lecture. So the question we want to understand is how do various patterns equilibrate and compete? And in order to understand those questions, what we need to consider is the nonlinear stabilization. So the way I'm going to do this is a complete hack. What I'm going to do is I'm going to start off by considering systems with sort of 1 degree of freedom, or a simple dynamical system, introduce you to the idea of bifurcation theory very crudely. We won't go into it in any depth. And then we'll sort of patch onto that some of the structure that couples different regions in space together, sort of gradient terms. And in this way, we'll derive the governing equations of motion. So the strategy, which is just to get us to where we want to be as quickly as possible, is we're going to start off with bifurcation theory. For 1 degree of freedom. And then couple the order parameter, if you like, at different points in space by some trickery using the linear stability analysis. So I emphasize this is only quick and dirty, and professionals do this in somewhat more systematic ways. You'll be relieved to hear. Okay, so that's our goal, that's our strategy. So let's get started. Let's have a look then at, let's suppose we have a dynamical system with 1 degree of freedom, which in the present context we can think of as being a velocity or something that characterizes the convection. So we're going to say that the dynamics of that is given by some function of u and a control parameter epsilon. And what we're going to assume is that for control parameter epsilon small enough, so that means epsilon is less than some critical value, then that u is equal to 0 is a stable solution. Okay, so that tells us then it's a stable solution and a steady state. So what we know then is that f of 0 and epsilon is equal to 0 for epsilon less than the critical value. Now, what we're interested in is expanding near the critical point to try to understand the behavior as we go through epsilon c. So near the critical point, what we're going to do is expand f of u and epsilon. And of course, this is in the spirit of Landau theory. In Landau theory, we also sat around the critical point, and then what we did was we expanded our free energy to the lowest non-trivial power. So let's suppose that we do that here. So then we're going to get that f of u is equal to a plus b u plus c u squared plus d u cubed, and so on and so forth. Now we know that u is equal to 0 is a solution of the of u dot equals 0. And so that tells us that the first term, a, has to be equal to 0. So that has to be true. Okay, so now let's see what else we can do. Well, the next constraint that we have is that that epsilon c is the critical point. So next, we know that for epsilon greater than epsilon c, we have an instability to a presumably periodic state. And so that must mean that that B itself must change sign around epsilon c. And in fact, if we have the equation u dot equals bu, if epsilon is less than epsilon c, that is we have a stable state. What that means is that b must be negative. So we can say that b is definitely less than 0 when epsilon is less than epsilon c. And b is greater than 0 for epsilon greater than epsilon c. And so from that we can see that we can write b as b naught times epsilon minus epsilon c plus higher order terms in epsilon minus epsilon c squared. And all we're going to be using here is we're just going to be using this lowest order term, something like that. And of course, in this expression, b naught is greater than 0. So then the next simplification that we can make is that there is a symmetry in the problem. So we can say that next we suppose that there's a symmetry, as there often is. And that symmetry requires that the results are invariant. And u goes to minus u. And we saw that, of course, in the case of a magnet, where you can, the magnet Hamiltonian is symmetrical, at least at 0 field, under all the spins being reversed. And so if we write the free energy in terms of the magnetization, it should only involve even powers of the magnetization. And so what that means is that if our equation has to be invariant under u goes to minus u, then that means that the term c must be equal to 0. Now, why is that? Well, because if it wasn't the case, then my equation of motion would be u dot is equal to bu plus cu squared, and the u squared would then stop the symmetry under u goes to minus u. So we know then that c is equal to 0. And so what that then leaves us with is a simplified problem in the vicinity of epsilon c. We know that then u dot we can write as some coefficient, I will call it r, times u, plus another coefficient d times u cubed. And r itself is just b naught times epsilon minus epsilon c. And d can be either positive or negative. And in fact, depending on that sign, we may need to have other terms as well. So there might be the next order term would be a term that is of order u to the 5th. Okay, so let's then have a look at what this tells us about the solutions. So if we now look for the steady states, then we can simply read off that u is equal to 0 if r is negative and d is, I'm going to say it all wrong here. So let's say if u is equal to 0 and r is less than 0, then that's a steady state, and this is the case where d is less than 0. On the other hand, u is if r is greater than 0, and u could be 0 or plus or minus 1 r over d to the 1/2. So this doesn't make sense. 1 second. Okay, back again. So this term here, of course, is r over the absolute value of d when r is greater than 0. So that's one of the steady states. On the other hand, if d is greater than 0, then it goes the other way around. U is equal to 0 is the only stable state for r greater than 0, the only steady state, and r could be 0 or r over minus d to 1/2 when r is less than 0. So what kind of state we get depends on the sign of d. So let's just draw this as a sketch. So what we're saying is this: if I were to draw my control parameter on the horizontal axis, and here is the value of u that I can get, then what we expect is we can either have a situation when we come along like this, and then we get either one of these two solutions, like so. So this would be called a supercritical bifurcation. Now the other picture that we could have is something like this. So here is r like so, and we're going to draw then the shape of the curve. So I'm going to draw the solutions. So it's going to bend backwards like this. Like so, and then the solution, strictly speaking, looks like this. But the actual behavior that you observe is you would come along like here, and then you would jump up to here, and then you would follow this trajectory like so. And so in this particular case, you would then have a subcritical bifurcation. And in fact, you would have hysteresis depending upon whether you were going up in R or down in R. And so this is the picture that this simple analysis tells you. And we can think of this as being kind of like a second order transition, or continuous transition. In phase transition theory, and this would be something like a first order transition. Okay, so that's the basic picture, that we can expand a system with a low number of degrees of freedom in terms of its parameters. And one thing I didn't say in this particular case here is that you would need, for this particular case where this pitchfork goes backwards, you would then need to have a higher order terms in order to get the picture that I'm showing you for the subcritical bifurcation. Okay, so that's all for just one degree of freedom. And now let's ask what happens when we include spatial extension. So what I want to imagine that we now have a variable that's not just a simple scalar, but is a field, maybe a vector field, that now depends upon x as well as t. And we're going to assume that, for example, that this field orders along the x direction. So then I can write that u is going to be proportional to some amplitude a times a wave e to the iqx in the x direction plus its complex conjugate. And let's suppose we just focus on one particular component. Then we might say that u will, every component of u will have an amplitude and a phase. So what we would expect then is that we would write that the x component u, we'll call it the scalar u, would then be written down as some amplitude, absolute value of a, and then x or e to the I qx plus I phi plus complex conjugate, and this phase phi is important because it is in fact a variable that is relevant to the translational invariance of the system. So the physical significance of phi is that it generates Galilean transformations. And what I mean by that is just a simple translation of the system. So let's suppose, for example, I had a picture of the system looking something like this. So here's my system, and I were to draw the maxima of the pattern. So let's denote those like this. And so in between these things, we can think of the wave as going like so. And now suppose that I were to make a shift in the origin. So basically what's happened is x has gone to x plus some x naught. Then that is going to end up giving you a phase shift by amount qx naught, like so. And so then what happens is I've now got a situation where the wave has been translated. That's shown over here. This distance here is q x naught. So in other words, the phase invariance is the same thing here as translational invariance. And so if our original equation was indeed phase, was indeed translational invariant, then our description of the system should be invariant under phase. So what does this mean? What that means is that if we want to look at the equations governing the complex amplitude, AE to the I phi, this must be invariant. Under phase rotations if the original system is translationally invariant. And so we expect there to be a global U1 symmetry, O2 symmetry. So if I were to write down the equation of motion for the amplitude as a function of space and time, well, we're not going to worry so much about the space for the next minute or two, but what that's got to look like is it certainly has to change sign at epsilon c. The amplitude of this wave has to be zero below epsilon c and non-zero above it. And then the next term that has to come out has to be something like d times a times the absolute value of a squared. So whereas before, for the scalar case, we just simply had u cubed, now we're going to have a times the absolute value of a squared. Okay, so this is great. But we've left out the gradient terms. And so now let's figure out what those gradient terms are. So as I said, one could do this by some fancy renormalization group way, which we're not going to do. What we're going to do, and if you, by the way, if you want to do this, so the RG way to derive the equation for the wave amplitude, or the pattern amplitude, that's described in a paper that I wrote, Chen, myself, Yoshi Ono, in PhysRev E, 1996. Anyway, we're not going to do that. So what we're going to do here is use a simple heuristic argument. And it's not a choice of heuristics or the normalization group. There are singular perturbation theory methods which are perfectly good, but exceedingly complicated, as complicated, if not more so, than the normalization group. And so I'm just going to use this heuristic method. So here we use a heuristic method that uses only the dispersion relation from linear stability analysis about a uniform state. So the setup that we want to deal with is this. So we're going to imagine, so what we're going to consider is the system with rolls, convection rolls, parallel to the y direction. So something like this. And this would be the x direction. This is the y direction. And what we're going to be looking at is the envelope that this system experiences. So we're going to imagine that if I were to plot the function of space, the order parameter, it's going to look something like this. with some spatially varying state. And what we're interested in is the amplitude. I'm drawing you here. So this is the function A as a function of space and time, and the pattern itself is the thing that is varying as e to the I q x, like so. And in practice, what we'll be doing is looking at a pattern varying at the mode frequency qc, where the linear stability problem has the following dispersion relation. Looking something like this. So what we're expecting then is that in this pattern over here, the wavelength of the pattern is about 2 pi over is about 2 pi over qc. Okay, so let's so the trick to doing this is to consider the form of the dispersion relation. And then what we're going to do is we're going to go backwards from the method that you saw in quantum mechanics, where you start off with some spatial operators or some time and space operators, and you go to variables omega and k. So what we're going to do is we're going to start off with omega and k, and then convert those into differential operators. So we're going to consider the form of the dispersion relation omega as a function of q, and then from that, what we're going to basically say is that omega is going to go to something like a d by dt, and q is going to go to something like I times grad. And so if we know the dispersion relation, then we can write down a differential equation that it came from. So in other words, knowing omega of q enables us to write down a linearized PDE for small perturbations. And so that's the way that we're going to construct the spatial structure here. So let's ask ourselves then, what does omega of q look like? Well, just from what we have over here on the left, you can see that it has the form of some kind of parabola centered on QC. So I'm going to write omega of q in the following form. Well, omega has the dimensions of inverse time, so I'm going to write it as some inverse time scale like that, and then I'm going to write it as a constant r minus xi squared q minus qc squared plus order q minus qc cubed. Something like this. So this is just a functional form which is peaked around QC, and the motivation for this is that the dimensions of omega are inverse time, and the dimensions of Q are inverse length, and so we have a time scale tau and some kind of spatial scale xi. Like so. So, and when I write down R, of course, as before, R is just equal to epsilon minus epsilon c. and so we'll change sign. And so as long as R is positive, then our graph will look like what I have over here. If R is negative, then the curve will be fully below the 0 point, and everything will be stable. So the way that the argument works is to take our particular state, our pattern state, and modulate it by a spatial amplitude with some structure, with some wavelength q. So the strategy now we're going to use the uniform dispersion relation. But what we're going to do is we're going to take the pattern with wave number q, and we're going to modulate it by multiplying by the amplitude times a wave e to the I qx x times e to the I qy y. So we're going to apply this perturbation to our pattern. And so what that means is that when we write down the vector q as qc and 0, that's how it started off, it's going to then become, under this modulation, it's going to become q is equal to qc plus qx, and then 0 plus qy. So it's going to make that transformation. And what we're going to do is plug that into our dispersion relation, omega of q. So that's the idea. So when we do that, what's going to happen is this. Let me write it down in terms of tau omega of q, which is dimensionless. So that's going to then become this. It's going to be r minus this length scale psi squared times the square root of qc plus qx squared plus qy squared. All of that is under the square root, minus qc, and then this whole thing squared. And that's all I've done then is I've substituted that into this particular form that we have over here on the left. Okay, so let's do this, and now let us then expand the square root. So I'm going to write this as being approximately equal to r minus xi squared into qy squared over 2 qc plus qx, and this whole thing squared, like so. So that's just expanding this out, and so what that means is that if I write down what my pattern looks like now, so it's a function of x, y, and t, and that's going to look like the following. So it looks like a is a function of x, y, and t, e to the I qc x plus its complex conjugate. And now substituting this form in, what we're going to get is the following expression, a naught e to the omega q times t e to the I qx x plus qy y times e to the I qc x plus its complex conjugate. So far I've made no approximation, and then what we would do is substitute the formula above into this result. Now, so this is exact, and then what we're going to assume is we're going to make the identification that omega of q is basically a time derivative, qx is a spatial derivative with respect to x, and qy is a spatial derivative with respect to y. And so now when I plug that formula into what I have above, then what I end up with is this, that tau d by dt of A is equal to Ra plus xi squared d by dx minus I over 2qc dy squared, all of that squared acting on the operator A. So my claim is that if I have this linear differential equation, this linear differential equation has as its dispersion relation, when I Fourier transform it, equation star, and that's easy, is easy to see. Okay, so that's just the linear term here. So remember what we were trying to do was we were trying to add the gradient terms to the terms that we already got from bifurcation theory. So over here on the left, we have the bifurcation theory plus the gradient terms. And now I've just calculated, at least to linear order, to first order in amplitude, what those gradient terms look like. And you can see that I get a linear order, I get a term linear in A, just like this term over here. And then I have these extra gradient terms, which we didn't have on the left-hand side. And then we have the nonlinearities, which I have on the left-hand side, but not on the right-hand side. So if we now put all of these things together, then what I end up with is tau d by dt of A. Then I have the term Ra, which was in both the bifurcation theory expression and the Landau theory expression and the gradient terms. Then I have the nonlinearity, which preserves the phase invariance. And then I have the gradient term, which has some length scale in it times dx minus I over 2qc dy squared acting on A. And that then is the equation that supposedly should govern space-time variations of the amplitude of a bunch of rolls moving in the x direction. So my claim is that if I look at this picture over here, I've taken a snapshot of my physical system. I see that the amplitude is spatially varying. The amplitude itself obeys not the Boussinesq equations, but the equation shown on the left. So let's just write that down in a crystal clear way. So this is the velocity field. This is u, which obeys the Boussinesq equations. And then this thing over here is the amplitude. And that obeys the so-called amplitude equation. Which is the equation that we have on the right-hand side. And this equation has a name. This equation was first derived by Newell, Whitehead, and Siegel. It's also, and this was derived sometime in the sometimes the 1970s. One thing you may notice about this equation is that, of course, it's a bit scary. You notice that it is, of course, not symmetrical in x and y. So let's just make a quick comment about that. note that the Newell-Whitehead-Siegel equation is not symmetric in X and Y. And the reason for that is because we're looking at the stability of rolls going in the X direction. And that's because we are expressly interested. Well, that wasn't great, was it? Why does this always happen? Okay, well, we somehow got things back. And this is because we are expressly interested in rolls along Y. And so you might ask, well, okay, this is fine. So that obviously breaks rotational invariance. And you might ask, well, can we write down a form of this that that doesn't break rotational invariance? And so let me just say that there is a rotationally covariant form of this amplitude equation. And that was first written down to my knowledge by Urbana-Champaign and Swinny and Uyong Shi. I'm not sure what order. Sometime in the middle 1990s, and also derived by Graham from my own RG method. Actually, it's quite an interesting story. If you use renormalization group and just renormalize the most leading divergences, you get the Newell-Whitehead-Siegel equation. If you renormalize all 8 divergences, which I was too lazy to do, then you get the rotationally covariant form of it. And there's of course a trick to deriving that using this simple heuristic method. And I'll post a homework sheet that enables you to try that out for yourself, so you can do this. Okay, so now we have a have this amplitude equation, and now we want to talk about what we can do with it. So the main things that I'm going to be interested in are not sort of solutions of it per se, but I'm going to be mostly interested in scaling properties of the amplitude equation. So that's what we're going to talk about now. So the first thing is that when we write down an equation like this, of course, if it's going to make any sense, all the terms have to be of comparable order. And when we what do we mean by comparable order? Well, we're looking at scaling properties as we vary epsilon. So they must be of comparable order in terms of the variable that is the only one that really matters, which is epsilon minus epsilon c. So just like what we were trying to do in superconductors and superfluids and so on, we're looking in the vicinity of the critical point. So let's have a look at the balance between these different terms. So what we're doing now is what in asymptotics would be called a dominant balance type of argument. So let's have a look at the balance. So we can see that straight away that tau d by dt of A has to be of the same order as R times A. So that's an order epsilon minus epsilon c. On the other hand, if I look at the term psi squared times dx squared of A, that also has to be of order epsilon minus epsilon c. On the other hand, the term xi squared over qc squared dy to the fourth of A, that also is of order epsilon minus epsilon c. All of these terms have to be comparable. And so what we can see is an interesting anisotropy in this problem. So this implies that we can estimate that spatial derivatives in the x direction of this pattern scale like epsilon minus epsilon c to the 1/2. Okay, that's one derivative, and a derivative in the y direction is something like epsilon minus epsilon c to the 1/4 times A. So in other words, phase variations along x obey something like a diffusion equation. But phase variations along y obey an equation that looks something like this. And some of you may recognize this. This is sort of like a bending beam equation. So if you have a rigid beam, not a string, but a beam of finite thickness, and try to bend it, because of the way the different elements in that beam interact, instead of it having obeying a sort of diffusion or harmonic oscillator equation, it obeys an equation with a fourth derivative, and that's exactly what you're seeing here, and that's because the rolls along the y direction have their own emergent stiffness. If you will, their rigidity, and basically, you know, the reason where this comes from, the origin of this is simply that if you want to you know, work out what is the you know, what is the energy cost, the reason is that the energy of a bent beam is basically proportional to its curvature squared, and because it's a curvature squared, that's where the fourth, that's really where the fourth derivative comes from. Okay, so I told you that I was interested in the scaling laws, so we haven't really quite got the scaling laws yet, but let's get there now. So what we're interested in, so our goal in this section was to look at space-time scaling near this bifurcation point epsilon c, and so what I want to show you now is that there I can rescale everything to get a universal equation. And so let me go through that. So let's start off then with our amplitude equation in this form. Okay, so there's my equation, and I'm going to basically do dimensional analysis on this equation. So the dimensions of time, those are set by tau. The dimensions of space are set by xi, and the dimensions of the order parameter, the amplitude, is set by r over d to the 1/2. So what that means is we can rescale in terms of these variables, and so I'm going to rescale in the following way. Capital X is going to be defined as the square root of r over xi times x. Capital Y is going to be defined as r to the 1/4 over xi over qc to the 1/2 times y. Capital T for time is going to be r over tau times t. These powers of r come from the scaling on the previous page, and then my new dimensionless order parameter or amplitude is as r over d to the minus 1/2 times times a. So if I make those changes of variables, then you can quickly verify this, that we get an equation that says, whoops, that's not exactly what it says. It says d by d capital T of capital psi is equal to psi minus psi squared plus d by dx minus I over 2 d by dy, and these are all capital, times this thing. And this is an equation, a universal equation with no adjustable parameters. And you can do the same thing, by the way, in superconductivity or in superfluids. So this apart from the anisotropy, this looks just like the Gross-Pitievsky equation, except that has an I in it from quantum mechanics, or it looks like the equation you get near a critical point for a superinductor. So This equation describes all the spatial variations near the threshold to the formation of walls, and so what is the interpretation of this? Well, just to belabor the point. So what this means is that spatial variations transverse to the walls relax with a characteristic length scale which is order 1 in the variable capital X, and i.e. xi over r to the 1/2 in the physical coordinates. And you'll probably recognize this because remember r is proportional to epsilon minus epsilon c. And so what that means is that the characteristic length scale, this correlation length as a function of epsilon, scales like epsilon to the minus 1/2, and in fact diverges near the point of instability. Just like we have seen in superconductors and superfluids. If we, on the other hand, we look at spatial variations along the walls, have a characteristic length scale which is of order 1 in the y units, and so in physical units, it's something like order xi to the 1/2 over qc to the 1/2 r to the 1/4, and so this goes like epsilon minus epsilon c to the minus 1/4. And similarly, if I were to look at the timescales, that's on the scales of order tau over r, i.e. delta epsilon to the minus 1 power. And so this is, again, extremely similar. The same results happen near a critical point in a phase transition. So these are the divergence of these space and time scales near the critical point at the onset of convection is precisely analogous, at least in mean field theory, to the mean field theory of critical phenomena. And I didn't mention this, but the order parameter itself, I forgot to mention this, and I should have put this in. So let's see if we can squeeze it in up here. The order parameter scale is again of order r to the 1/2, which is again like a magnetization growing as T minus TC to the 1/2 below TC in critical phenomena, at least in mean field theory. Okay, so that's shows you this the power of this approach. So one comment is that it is possible, but very hard, to constrain these experiments sufficiently that you can see thermal fluctuations. These things are very hard to see, but not impossible if you have brilliant experimentalists like Gunther Alles and collaborators. So this has been done in a real tour de force. I'm just going to drop the reference here. Alles and Cannell, all of whom are just absolutely fantastic experimentalists, and this was in Physical Letters 1995. So it is possible, even in these non-equilibrium systems, to see these thermal fluctuations. So I think that's where I'm going to leave things. I think that what I don't want to do is I don't want to go into looking at what happens in great detail below threshold. So let's just make a sort of last comment about this, but I'm not going to go into details here. So let me just say something about emergent patterns well below the threshold. So up to now, so far, we talked about the behavior near the critical point, or the point at which we start to see convection. So now the question is, what about epsilon much greater than epsilon c? So we're well into the pattern phase. And if we were to reason with what we already know, so what we would guess is something like this. What we would guess is that the amplitude of the pattern is saturated by the nonlinearities. And so the amplitude basically A is basically a constant. But then the only remaining degrees of freedom are the phase degrees of freedom. And this is exactly what we saw in equilibrium. This is exactly analogous to what we saw in equilibrium, and like what you did in homework 7, for example. So what I want to just say is I just want to summarize what one can calculate. So the phase dynamics can be worked out. and actually near the threshold, you can work it out fairly simply. I'm not going to um, I'm not going to bore you with the details. So let me just say that near threshold, the phase dynamics obeys the equations like so. The phase dynamics are diffusive, but of course the phase dynamics are diffusive with different rates in different directions. So it turns out that d phi by dt is equal to some d parallel in the x direction and some d perpendicular in the y direction. So I've got anisotropic phase diffusion because I've got rolls that are anisotropic, and d parallel turns out to be xi squared over tau times epsilon minus 3 xi squared k squared over epsilon minus xi squared k squared, and d perpendicular is xi squared over tau times k over qc, and the k that we're talking about here is a state which has been perturbed by a wave number k. So the value k is the wave number of the state minus the critical q value qc. So this is the wave number of the pattern. So this gives you a so remember remember that we are well away from QC. And so we have a very large band of unstable wave vectors. So here's Q, here's our dispersion relation. So usually what we're interested in is something like this, where this is QC. So that's this is the case where epsilon is just slightly above epsilon c, and now we're in the situation where epsilon is a lot bigger than epsilon c, and so we have a whole band of unstable wave vectors like so. Okay, so that's the anisotropic phase dynamics, and if we go even further away from the critical point, we end up with a much more complicated equation, and which I'm not going to derive, and that is the cross-neural equation. So by an equation describing the space-time variation of the local wave number. And so basically you have a phase, a generalized phase, which varies in space and time, and you can work out how it does that. And it's really quite complicated, and that's an equation due to Mike Cross and Alan Newell. And that's sometime around the late 1980s, if I remember right, or early 1990s. Okay, so that is where I'm going to stop, and hopefully this introduction to patterns has been enough to whet your appetite and show you that even though you have non-equilibrium problems, one can do a lot in terms of understanding their behavior. And I talked here about problems in fluid mechanics and convection in particular, but there's many other phenomena, not just in fluid mechanics, but even in electronic systems where hydrodynamic instabilities and pattern-forming instabilities happen, and those one example is the high-temperature superconductors, as we've mentioned already, and this is really very much a frontier area of kinetic physics. So with that, farewell.